This is a video about artificial intelligence, which I am giving in my YouTube video channel called AI Nexus. I am Dr. T.V. Geeta, and I'll be talking in this particular video about overfitting, bias, and generalization, which I will explain quite simply in a simple manner. So first, let us understand what is inductive learning and its connection to machine learning. So machine learning, as you remember, is to learn patterns from data instead of being explicitly programmed. So fundamental here is that the algorithms that perform inductive learning from data, this is also called the bottom approach. This is the basis of machine learning. Now, a key assumption in machine learning is that whatever is observed in the past will continue to be true in the future. Otherwise, we cannot do inductive learning or learning from data. Now, let's take an example. You have specific example of mangoes. So we observe the mangoes, observe the features like it's yellow in color, it's kidney shaped, and it's tasty. And then we form rule about it. And then when you're given a new example, you're able to find those features, yellow, kidney shaped, and sweet, and probably assume that it's a mango. Another example is the student study pattern. So I have a student studying for 1 hour. He does badly or poorly. Another who studies 3 hours, who does reasonably okay, and one who studies for 5 hours, who performs very well. So from this, there's an observation that is, and we get a rule: the more study time, the better the performance. So you're given a new data that a student studies for 4 hours, we can conclude that his performance will be good. Okay, so now let's connect this with inductive learning and machine learning. So we begin with observations, that is the data. In machine learning, this is called training data. Then what we do, we detect patterns and regularities in this data, the features associated with this data, and you formulate some tentative rules. In machine learning, this is learning a general model, a learning model. And then finally, we have prediction. We predict on the new data. In machine learning, this is called predicting on testing data or testing the model. Now, let's go to another term called generalization. Now, what is this generalization? Machine learning, as we know, again and again, we are telling, is about finding patterns in data. So generalization is the ability of the learning system to apply what has been learned in the past, the training time examples, and to apply it to unseen situation that we are giving it at test time. So this is generalization. And generalization is a central concept in machine learning. So machine learning is not about memorization. Memorization plus is actually perfectly working on training data during memorization, but it will not work well on training new data. So learning plus capturing underlying patterns, this will give rise to good future predictions. So a machine learning model, if it has learned well, it means it generalizes well. So it is learning the rule, it is not learning to memorize. So the true goal of machine learning is generalization, not training accuracy. Okay. Now we'll go to some terms which sound a little complex, but actually it is simple if you understand. This is called overfitting, underfitting, and good fitting. You can actually think about, your dress or something when you think about this. That's a good analogy to understand it. So first we'll talk about overfitting. Overfitting is memorizing too much. That means you're also learning understanding the noise, learning the noise. So it is bad generalization and the model is too complex. Now the other side of the coin. Let's look at underfitting. In underfitting, what you do, you didn't learn enough, not too many details. So it misses all the patterns. Again, bad generalization and the model is too simple. What we actually need is good fit. That means good learning, good generalization, and it's a balanced model. Now, there is a guiding principle in machine learning, what is called as an Occam's razor. That means if you have choice between simple model or simple explanation, in our case model, and complex model, you choose the simplest model that actually fits the data. That's approximately fits the data. Now, both overfitting and underfitting will lead to poor predictions. Okay, both on new data sets. So, does not generalize well. While a well-fit model actually learns the true patterns from the data, not the noise, and it is able to have low training error as well as to low test error, and this is the best generalization. So this is about overfitting, underfitting, and good fitting. Now, associated with this are two terms called bias and variance. Now, variance is the error caused by excessive sensitivity to the training data. That means it's exactly following the training data. So a small change in the training data, what will happen? There will be a big model change, and there will be testing error. Because the model will also fit noise. This is what is overfitting, leads to overfitting. So high variance means overfitting. Corresponding, the other term is bias. Bias is the error because caused by overly simple assumptions in the learning algorithm. So model cannot capture the true pattern. So there will be training error, which leads to underfitting. An example of this is actually you have a nonlinear relationship in the data, but you actually capture it as linear. So high variance means underfitting. So overfitting means low bias, high variance, and training data accuracy will be high in the case of overfitting, but testing will be, accuracy will be poor. Now, if you take underfitting, it will be higher base, higher variance, training data will be, accuracy will be poor, as well as test data accuracy will also be poor. So good fit, you should have low bias, low variance, where training and testing accuracy both should be high. Now, so what we come to what is called a bias-variance trade-off. As a model complexity increases, the bias decreases, but variance increases. So you have to find a sweet spot where the total error is minimal. So the bias variance cutoff is the optimal balance point where the sum of the bias and variance error is minimum. This results in the lowest testing error, because finally we want to predict, we want the lowest testing error. Now, if you take machine learning from, we are just concluding what all the terms we have to make it easier for you to remember. So you have generalization, where the ML performs well on unseen test data. Now, if you have bias, you have made simply you have made the wrong assumptions. So high bias means the model is too simple and it leads to underfitting. We'll come to that. Variance, there is high sensitivity to data. So high variance means model changes a lot with data. Now, when there is high bias, there is underfitting. So there will be high training error as well as high testing error. When variance is high, you have overfitting. There will be low training error because training data is exactly fit, but there will be high testing error, which we don't want. So you come to the bias variance trade-off. So you have to choose the optimal model complexity. So good generalization means low training error as well as low test error. That's what we want to achieve. Now let's take two examples to explain this a little bit. One is learning to ride a bicycle. In high underfitting, where you have high bias, you just pedal randomly without balancing and you may fall down. Now overfitting means you learn to ride only on a very nicely on a smooth road. What will happen? It will learn, but it will struggle on bumps. So actually a good generalization will be, you have to learn to balance, you have to learn steering, and you must be able to ride on different roads. That's a good generalization. Another example is learning to play cricket. All of you will understand this. Underfitting means you learn only to hold the bat in nice way, but you cannot score runs. Overfitting means high variance, practice only on one type of ball, so but fails against new deliveries. Now what you have to do, you have to learn timing, you have to learn shot selection, you have to read the bowler, only then you can actually score runs. So you have to learn the pattern, overall pattern. So that is a good generalization. Now let's look at some good and poor machine learning problems. Now let's look at pattern recognition. When the pattern recognition is complex, for example, face recognition or handwritten images, then the pattern recognition is complex. They are good ML problems. But you have pattern also in email format. But there it is deterministic logic. So it's a bad problem. Now you look at acceptable and zero error. Movie recommendation, error is okay. So it's a good machine learning problem. But if you look at medicine dosage, here error is not to be tolerated. So it's a bad machine learning problem to take up. Data availability. You cannot do machine learning without data. So if you predict customer churn, past customer data is available, you can get it. So it's a good machine learning problem. But if you want to predict rare disturbance, natural disturbances or disasters, you don't actually have data to predict. So you may not get good prediction. And then does the problem improve with more data? If you take speech recognition, the more the data is better accuracy. But when you're doing something like sorting numbers, having more data does not increase your availability. Okay, or I'm sorry, it does not benefit from more data. Now, ethical and risk sensitivity for fraud detection, you can do human checking, but automatic present sentence, once you do not involve human in the cycle, you are at ethical and legal risk. So this, we have told you about some of the topics and some of the good and bad problems that you can find in machine learning. Thank you.